Welcome to the first of two discussions on queues. This is our third data structure. We talked about lists and stacks last time, and now we're going to talk about queues. So what are queues? Well, queues are basically a way of modeling waiting in line, whereas other places, other English speaking, they actually call them queues. So it is a way of supporting fair processing. Imagine if you used a stack instead of a queue, which was last in, first out. So if you got into the stack and you were waiting to see the service rep or buy the ticket or whatever, and someone shows up, they go in front of you. And if someone shows up, they go in front of you. And then they get processed. If someone shows up, they get in front of you. So you may never see the person or get service. So a queue supports fair processing because the first served is usually the one waiting longest in line. The person at the front of the queue got there first, or most recently. So it's first in, first out. You get added to the rear or end of the queue, you work your way through to the queue until you're the front, and then you get service at the front. And there's another criteria, is there's no cutting or saving spaces for your friends in line. So if you get added to the end of the queue, you know that you will get to the front of the queue as they get processed. There's no people sneaking in the middle of the queue. So they're basically, the queue interface is a simplified interface from the list interface, and it does extend collection, so we have to supply the collection methods such as size and is empty and contains, and also collection implements iterator, so queues also have an iterator over the items in the queue. And so the first method is basically the collections add method, which just says you add at the end of the queue or the rear of the queue. And potentially this will throw an exception if you try to add the wrong kind of item, or if there is a fixed size on the queue and you cannot add another thing to the queue because we've exceeded the size. The offer method is similar to the add method. It's just another naming. Again, we're adding something to the end of the queue or the rear of the queue, and again, may throw an exception if the item is not the right kind or there's an issue with the size of the queue. The element method retrieves but does not remove the head of the queue. If the queue is empty, this method will throw an exception. The peek method is similar to the element method, as it looks at the head of the queue, does not remove the head of the queue. It's like the peek method for a stack. If the queue is empty, peek returns null and does not throw an exception. So it's very similar to the element method, except for it doesn't throw an exception. It returns null if the queue is empty. Poll is similar to peek, except for it removes the item in the big front of the queue, or returns null. If the queue is empty, it will return null. So that's how you know that the queue is empty. But if the queue has elements in it, it will remove the front of the queue, making the queue one shorter. The remove method is similar to poll, except for when the queue is empty, remove will throw an exception instead of returning null. So let's look at a couple of implementations of the queue interface. The first implementation uses the Java linked list class to hold the data. One of the reasons we're doing this is the linked list class actually implements the queue interface, so it has all the methods we need. One reason why you wouldn't just use a linked list when you're trying to model a queue is the linked list is a list, so you can insert in the middle of the list, you can get items in the middle of the list, you can remove items from the middle of the list, and those functions are not supported by the concept of a queue. You can only remove things from the front and add things to the rear. So a linked list, if you just use a linked list, the person might use the methods that are not defined for a queue. So in this case, we create a private linked list to hold the data, and the constructor, we just instantiate the linked list. Now we don't have to keep track of the size because the linked list keeps track of the size, and the linked list is going to basically do all our work. So now we can just implement all the queue methods by delegating them to our linked list. So for example, the add method in the queue adds an element at the end and returns true. It also will throw an exception if there's a problem, but in this case the queue will grow, so there's no problem. The offer method, again, the queue has an offer method that does the right behavior. It will return true and add the item to the end of the queue or end of the list. The element method, again, since the linked list does implement queue, the element method will check and see if the queue is empty and throw a no such element exception, or return the value at the front of the queue. The peek method does the right thing. It checks to see if the queue is empty and it will return null, or it will return the first element or the beginning first thing in the queue, but it does not remove the first thing. Poll removes the first thing from the queue, and if the linked list is empty, it returns null and also decrements the size correctly. Remove does the correct things and throws the exception. So we simply just delegate all the methods to the linked list instead of having to actually implement them ourselves. A second way of implementing the queue is to actually do the implementation using a singly linked list. So in this case, we're going back to our old friend, the node. In this case, a singly linked list, a singularly linked node, which has a data element to store the data, and a next pointer that points to the next node in the list or in the queue. We keep track of the front and the rear, and we also, since we're implementing it, we have to keep track of the size. So our default constructor, we set head to null, we set tail to null, and the size of the queue is empty. When we add an element to the end of the queue, we check to see if the front is null, which means that we have an empty queue. If it is empty, we point rear to the new node. So we create a new node and point front to rear. If front is not null, we just point rear dot next to the new node, move rear, and in both cases, we've added a new node to the queue at rear. So we increment the size and then we return true. Very reasonably straightforward. The tricky bit is here at the beginning when the queue is empty, you need to set up the rear and the front. Whereas when the queue has things in it, we just have to put a new node at the end and move rear. Offer does the exact same thing. No changes whatsoever. We could actually call add if we wanted to, just to make it simpler, but we could re-implement all the code. It's a fairly simple method. The element looks at or retrieves the head of the queue and throws an exception if the queue is empty. First we check to see if the queue is empty by checking to see front is null. If front is null, then the queue is empty and we throw our exception. Else we just return front.data, which is the first element in the queue. We're not changing the queue in any way, we're just looking at the beginning of the queue. The peek method is a slight modification of the remove method in that we don't throw the exception if the queue is empty, we return null. And so we just changed the one line from throwing the exception to returning null. And then if the queue has elements in it, we just return the front element. The poll method is similar to peek in that if the queue is empty, poll returns null. However, we do need to modify remove the item from the queue if it's not empty. So we remember the front item, we then move front to front.next, and since we've now shortened the queue by 1, we decrement the size and we return what was at the head of the list, or excuse me, head of the queue. The remove method is similar to poll, except for it throws an exception instead of returning null if the queue is empty. So again, we throw the exception if the queue is empty. We remember if it's not empty, we remember the front item, move the front pointer to front.next, decrement the size, and then return the item. And that is our second implementation of linked lists of the singly linked queue, Next time we'll talk about using a circular array to implement the queue interface. Thank you for your attention.